Good morning, everyone. Tim Sander. I'm a program manager on the Azure Cosmos DB engineering team. And I hope everyone's had their coffee and are awake, because today we're going to be building an event-driven app together using Azure Cosmos DB and Azure Functions. Just to show of hands, who's used Azure Cosmos DB before? All right, good. Who's used functions before? Perfect. So this is a level 300 session, so we're going to skip a lot of the basics and really dive into the interesting stuff. Today we'll be focusing on the change feed in Cosmos DB and how this integrates really nicely with Azure Functions. We're going to build together, throughout this 45-minute session, a sample app for a made-up airline called Contoso Airlines. The first thing we'll do with our app is ingest data in real time. And we're going to ingest data for Contoso Airlines' fleet of airplanes. We're going to ingest their location data. So basically, a document that has a latitude, longitude, altitude, and things like that of the plane. Once we've ingested that data into Cosmos DB, we're going to go and use it to send alerts if a plane enters a no-fly zone, and then display a real-time map of plane locations and display an upcoming arrivals board for each airport to show the upcoming arrivals that are coming soon. So our first step is just to figure out how do we want to ingest all this data into Cosmos DB. Now, when you ingest data into Cosmos DB, it's going to be a JSON document. So you likely have some sort of on-prem technology that would initially pre-process the data and eventually maybe send it to a function that goes and writes it to Cosmos DB. And you'd end up with something like this, a JSON document that has a unique GUID for the plane, the timestamp that the location data was sent, the plane's current altitude, the latitude, longitude, destination, and so on. So this is a plane going from Seattle to Orlando Airport, and it's a red eye leaving at 10 p.m., arriving at 7 a.m. So this will be ingested into basically our locations container. And the first thing that we do anytime we create a container in Cosmos DB, as you all probably know, is pick your partition key. And this is absolutely critical for an IoT application like this that's going to need to scale pretty significantly. So I'm sure since you've all used Cosmos DB before, you're pretty familiar with the characteristics that make a good partition key. You want your partition key to have a high cardinality, and it should also do a really good job at evenly distributing reads and writes. And it's helpful in a lot of cases for read-heavy workloads if the partition key is included in the filter of your most frequent query, right? Is this container, the locations container, where we're ingesting this data, is it read-heavy or is it write-heavy? First question of the day. And I have some prizes. So volunteer. Right, yeah. Right heavy. Try my luck at throwing? All right, that was a strike. Perfect. So it's right heavy. So because of that, we don't really care about the partition key's value in issuing queries, right? So we want a partition key for this container where we're ingesting data to satisfy these three properties. So question 2, what should it be? Departure airport, arrival airport, the airplane's tail number, or a unique GUID for every single basically piece of data that we ingest into Cosmos DB. Yeah, the tail number. So the tail number is a good choice. It would do a pretty good job at evenly balancing requests and storage. What we really want here is a lot of cardinality. So we only care about writes here. We want something that will have a high cardinality so that when we ingest data into Cosmos DB, the total size of a Cosmos DB can grow really large because each partition key will be small, so we can just add on more partitions. Each partition in Cosmos DB can grow up to 10 GB, so we want to keep each individual partition key small. Arrival airport? Arrival airport has that same cardinality problem. Yeah, the ID, something that's unique for each document. Now, whoever shouted that, come meet me after. I have another prize for you. It's too far to throw. The ID is a really awesome property in this case to partition by. Now, it obviously provides absolutely no value for issuing queries, but it's really awesome for guaranteeing a high cardinality as we ingest data. So each data point that we ingest will have a unique ID property, so we'll evenly distribute throughput and storage and be able to ingest data quite well. So we'll partition on that, and as we ingest data into Cosmos DB, we'll automatically store it behind the scenes based on this property. Here's a super high-level view of our architecture here. Of course, if you were actually building this, there would be a lot more in architecture than just Cosmos DB and functions. But to keep it simple, since we have 45 minutes, we'll focus on these components. You're going to be ingesting data into the locations container directly, and then have different microservices, which in this case are just going to be Azure Functions, go and subscribe to the Cosmos DB change feed to then go and each do a separate and independent small task. So the first one we'll focus on today on building is the microservice which sends an alert if an airplane enters a no-fly zone. So this is the logic that we'll use to decide if the airplane is in the no-fly zone. So very simple. We've dumbed it down quite a bit since this is just an app we're building in 45 minutes. Any guess on what location this is? This is the convention center. So if the plane comes close to the convention center, we'll send out an alert that it's in a no-fly zone. Reality, this would probably be things like other airports and stuff like that. But to keep it simple, this is the logic that we'll use. We'll send out an email alert to, let's say, air traffic control in the airline and stuff like that. So I'm going to start off with the demo and then kind of take it backwards and deconstruct how we made the demo. Perfect. So I'm going to start off a data generator that goes and generates basically sample airplane telemetry. So it's just going to be those same documents, the locations, it's going to be writing them to our locations container. I'm then going to go and start my email alert function, and I'm actually just running this locally right now. Reason for that is we're going to be modifying this a lot throughout the session today, so I want to be able to quickly modify it and get it started again. So that'll get started. Of course, it's really easy to deploy functions, but we'll run it locally now just to keep the development experience quick. Next thing I'm going to do is come to Cosmos DB and take a look at my Cosmos DB locations container. There we go. If I come to scale settings here, I can see that my browser froze. There we go. Cool. If I come to scale and settings here, I can see that I partitioned on my ID value here. So I'm ingesting data based on the ID value and storing it behind the scenes based off that. Now note here, I provisioned this Cosmos DB container with autopilot mode. So when I set it up, I just decided I wanted a locations container to collect telemetry and partition on ID, but I actually didn't have to think at all about the scale of that. I simply set up this container with autopilot provision throughput, and it's going to automatically scale between 10,000 and 100,000 RUs for me, and I won't need to think about this at all. I just picked that really wide range that I want to scale between. It's really awesome because I'm going to be running this demo today and be pumping a lot of data into the locations container. But after I'm done with this demo, it might be a few weeks before I run it again. So Cosmos DB is automatically going to scale down for you to that lower level, so it's truly serverless. You don't have to think about scale. If I come to my items here, I can see the sample documents that I've uploaded into Cosmos DB. So these have been written to Cosmos DB. Again, it's just those sample data points. So this is a flight going from San Diego to Orlando. So I have a logic app that's connected to that Azure function. So every single time a plane enters a no-fly zone, I'm going to trigger my logic app, which is going to then go and send an email to me. So the function has been running for quite a while. And every time you see email alert here, it's not actually sending out an email alert. This is just every time the function runs, we output that email alert function ran. And there was another write to Cosmos DB. So hopefully I got one email. Perfect. I got one at 9:22. And I get an email that Contoso Airlines flight 621 entered the no-fly zone near Orlando. Let's take a look at how that works behind the scenes and kind of walk through code. It was actually really simple to implement this. When I created my Cosmos DB container, the partition key was really important. But other than that, there really wasn't a lot I had to think about. Same goes for the function. Functions automatically read from the Cosmos DB change feed, and I actually really didn't have to think a lot about how that worked, and I also didn't have to think about this function scale. This function uses a Azure Cosmos DB trigger. So every single time we do a write or an update to the locations container, we're going to trigger the logic in this function. We'll come and loop through all the changes here, and every time there's a change, if the aircraft is in the no-fly zone, we'll go and execute the logic down here. Now, the logic here, really simple. If the aircraft is in the no-fly zone, we go and build a payload that will then go send to a logic app, which we trigger through this, basically, line of code down here. And then that goes and sends out an email. So 1 down, 2 to go. We've alerted basically our customers and air traffic control if the airplane entered a no-fly zone. And we did that through a Cosmos DB trigger using Azure Functions. Now, Azure Functions behind the scenes was obviously, as most of you likely know, using the Azure Cosmos DB change feed. Now, the change feed in Cosmos DB is my absolute favorite feature in the product. You want to think of the change feed as basically a list of documents per partition in Cosmos DB by the order in which they were modified. So in Cosmos DB, if you're doing writes to Cosmos DB, like we're doing here, you can just read from the change feed to basically get a stream of the latest updates and writes that were done to Cosmos DB. There's one change feed per partition in Cosmos DB, so this is what allows you to scale really well as you basically have many partitions, a lot of throughput, and more data. You read from the change feed using the change feed processor library. And you probably noticed I wasn't using the change feed processor library to read from it with that function. Azure Functions is going to automatically use the change feed processor library for you. And you don't really actually have to worry a lot about how it works. So every single time there's a write to Azure Cosmos DB, we'll go and trigger the logic in the Azure function, as you saw, and send the email if we meet the criteria. But since this is a level 300 session, I do want to talk more about how this change feed processor library works behind the scenes. Now, of course, today we use the processor library through functions. And the benefit of functions is it's serverless. So we don't have to worry about scale. We just ran the function. We can go deploy it, and it'll scale automatically. But if you want more control over scale and you want some more control over reading from the change feed, you can go take the change feed processor library and go deploy it on your own. So wherever you want to host it, you can do that as well. And the great thing about the change feed processor library, no matter how you're using it, is it guarantees at least one semantics. It guarantees fault-tolerant reading of the Cosmos DB change feed. So this means if you're doing writes to Cosmos DB, in this case, if we're doing the writes over location data, we are guaranteed to process every single write at least once. So this means we're never going to accidentally miss processing an airplane's location. So we'll guarantee at least one semantics there, and that's really critical for mission-critical apps that need that guarantee. The polling of the change feed and the management of your checkpoints for where you are in reading from the change feed is automatically managed by the change feed processor library for you. In addition, Cosmos DB is going to have different partitions right behind the scenes, and the change feed processor library is going to automatically read these different partitions in parallel. Functions is going to do this scaling out automatically for you. So as Cosmos DB has more data, and as you're ingesting more data, functions will read these partitions in parallel. Now, it wasn't too important for this scenario, but in a lot of cases, we actually need some guarantees about the order in which we process documents. So you might want to do, not really critical here, but you might want to have a guarantee that says, as I'm writing documents for different planes, for a specific, let's say, tail number, I want to guarantee that I never process a document that was written later before a document that was written earlier. So you want the guarantee that if for a certain plane, if you do writes A, B, and C, you'll process them in that exact same order. And the way to guarantee that is by partitioning on that property. We guarantee that within a particular partition, we're going to process the changes in the order that they were written. The way the polling works behind the scenes is actually really cool. To the developer and to the end user, it's essentially a push model. Every time there's a change, we go and we trigger that Azure function to send the email alert. So functions is going to automatically check the locations container for changes. If it doesn't find any changes, it's going to wait a specified interval that you specify. And you don't have to worry about setting this up in the logic here. It just does this behind the scenes. If it goes and finds a change, if there's a write of a document to the locations container, we'll go and process that. And then immediately after we're done processing it, we'll check for a new change. And because there's no wait after you process the document, because there's no delay until you check again, this allows you to really stream data in real time into Cosmos DB and do a really good job at saturating your throughput and ensuring you're processing all these changes in real time. Now, after we go and process document B, we're going to immediately check again, but we don't find anything. If we don't find anything, we'll wait that specified feed pull interval before we check again. And there is a very small cost every time you check a partition's change feed where there's no data there. So pretty trivial, but there is a non-zero cost for that. So you have control over that feed pull interval and how long you want to wait before basically the times you check. After waiting, we'll check again. We find C, we process that, and basically it continues. All this is managed automatically for you behind the scenes. You don't have to set this up. When you use a function, basically all you need to know is you can pick that feed pull interval, but every time there's a write, your function will be triggered with the maximum delay of that feed pull interval. The next thing that we'll do is build out that map with the current airplane locations. So we built one of our microservices that goes and alerts if an airplane enters a no-fly zone. We're now going to build out the next one that displays a real-time map of plane locations. So we have two options for building this. We could go and recalculate the latest airplane location every single time someone refreshes the web app. Or we could build a materialized view that has the current location of every airplane, and then every single time there's a web app that needs to reference this data, we'll just go and call that. So we're not going to recalculate it every time, but we'll have that value persisted somewhere with the materialized view so that different services that take a dependency on this data can simply go and access that. So this is a sneak preview of a question that we'll think about in a couple minutes. Now, if we recalculate the materialized view, if we recalculate the basically current location of each plane as we do the writes to Cosmos DB, we're going to do it with this query against the locations container. And there's some alternatives to this query. You could probably do like a group by and find the max basically max timestamp for every plane and have that be the location. But this is one possible alternative that we'll consider, where you basically do an order by for a particular flight number and take the top value from that. Now, how many times will we need to run this query per second? Will it be run a lot or not too often? We run quite a bit. We're going to conservatively estimate 10,000 times per second. It's going to be run once per plane per every basically web app or service that calls into our Cosmos DB container. So every time we want to display the location for a particular plane, we'll have to go and query the entire location history and issue this query here. This query is going to be a cross-partition query, right? We partitioned down ID. That provided a lot of value for doing writes, but it didn't really provide a lot of value for doing reads. In this case, we'll need to do a filter and an order by. We actually could optimize this with a composite index in Cosmos DB, but as you'll see through this demo now, it's actually quite an expensive query. So I'm going to open up the Data Explorer here. And come to my locations container and issue a new SQL query. So again, I can just issue a query simply right through the portal, and I'm going to type out that query, select top one from C, where C.flight number is equal to Contoso Airlines 16, we'll just say, and then do an order by C.timestamp. So the idea is every time our web app wanted to obtain the current location for a plane, it would have to go and issue this query. And the query runs, it's pretty fast, and it just outputs that single document that has that plane and its latest timestamp. So this is an aircraft going from London Heathrow to Philly, and this is its current location, longitude, latitude, speed, and altitude. But when we go and we look at the RU charge, we find it takes about 35 RUs. Now this is fine if this is an ad hoc query you need to run every now and then, but this is going to be something that's really central in our application that tons of different web apps out there are going to go and call and reference. So we could have maybe dashboards displayed on websites, or air traffic control could be really frequently running this query for each plane. So we want to make this as optimized as possible. So while initially our writes to the locations container, that was a very write-heavy workload, this scenario is quite a bit more read-heavy. So let's think about what we could do to optimize that. So we have two options for building this. We could recalculate the latest airplane location each time someone refreshes the web app, or we could build a materialized view that basically persists the current location of each airplane. Which do you think we should do? Who thinks A? Who thinks B? OK, good. I don't know if I sold it well enough, but if you all said A, I would have just kind of given up at that point. Perfect. So it's B. We'll build a materialized view with basically the latest location of each aircraft. Now, who's familiar with the materialized view concept? OK, so about half the room. So it's basically really simple. We're basically taking the results of a query and persisting that somewhere. So if you find you need to run a query repeatedly over and over and over again, and it's the same query, the idea is you just pre-compute the results of that query and then go and store it somewhere. So then every time you need to access basically run that query, you can just go and do a simple lookup for the results instead of repeatedly needing to run the query over and over again. In many cases, the materialized view might compute something like an aggregate or provide a subset of the data. The idea is to optimize for reads and quicker lookups. You can process and build this materialized view by reading from the change feed, and we can do that really easily using an Azure function. So the idea here is we can display a real-time map of plane locations and anticipated arrivals, pre-calculate that materialized view in the function every time there's a write to the locations container. Then we'll go and persist that in a container called our current locations container. And any web app or any other service that needs to go and access that information is going to go and call directly into this. They're not going to need to go and ever use the locations container directly. Now, while we were reading from the change feed for the locations container, and we're doing that for our really frequent queries, there are likely a lot of instances where you would want to go and look at a No worries. Perfect. Thank you. I don't think it's on yet, right? It's on? Perfect. Cool. I was going to shout, and then I think my rating would go down by a solid star after that, after shouting. Something always goes wrong in sessions like this. The one thing that I have no backup plan for is the Wi-Fi. So that's been great. So mics, I can shout. Wi-Fi, you're kind of in a bad spot. So we'll keep going. So idea here is we built that materialized view in the current locations container, and we'll just call into that directly. Let's actually take a look at the cost for this. So I don't think there was anyone that said option A, recalculate this value each time. But if you were a developer that chose option A and went and did this, you would probably not be a developer anymore. You probably would be out on the market looking for a new job, because doing that would require about 351,000 RUs. This is a very rough estimate. Of course, you probably would have way more than 10,000 times you need to look up each plane per second. But in total, this is going to consume 351,000 RUs. So really quite a bit, going to be very, very expensive. Now, with the materialized view option, we're going to pay extra for each write. So we'll be doing writes to the location container, and then calculating the most recent value, and going and updating the current locations container. And this will obviously use more RUs than before, because we're doing double the number of writes. However, instead of each read costing 35 RUs, they cost 1 RU. Because we're going to do something in Cosmos DB that's called a point lookup. In Cosmos DB, a point lookup is when you go and look up a document by its ID value. So queries in Cosmos DB, if you write an efficient query, it'll be pretty fast and pretty efficient. But nothing in Cosmos DB is faster than just doing a point lookup where you have the document's ID, that key, and then you go and get the value. So we can improve our application pretty significantly with this materialized view. So let's actually take a look at how we would build that and walk through some code. So I've had the data generator actually pumping out data for quite a while. And I've stopped that earlier function. Now I'm going to start this new function, which goes and computes the materialized view. So let that run for a little bit and jump into the Azure portal. So obviously, the alternative to running this query over and over again is to go, instead of looking in the locations container, go and access the items that are in the current locations container. So when I access that, there we go. When I access the current locations container, I'm basically going to get every document by its ID value. So when I come here, I can do a simple lookup. That's always fun. There we go, cool. So it must have been because I didn't have the web page open for a while. When I come here, I can do a simple point lookup of the document, and I'm going to access it by its ID value. So when I want to access this container, I'm going to do what's called a point read in Cosmos DB, and I'm going to supply the ID value in read item async, basically that call, the Cosmos DB, and I'm going to supply the Contoso Airlines 905 ID value to then go and do that lookup. I'm going to be running this very frequently, and if I do this call to Cosmos DB, because this is such a small document, it's going to use about 1 RU in total. What would be a good partition key for this current locations container? Any guess? Yeah, the flight number, right? The flight number is really nice because that's going to be something we'll know about, right? If we're looking for a specific plane's flight number, we'll have it, and we can actually pass that into the call, the read item async call, and that's going to make that really more performant, so we'll be able to target a specific partition. So we obviously have this container also on autopilot mode, and we very intelligently chose flight number to be the partition key here. So this has been running for a while now, and been pumping out more data. Now, right now I have 2 microservices running. Well, I stopped the other one, but I had it running before. And each one has a separate lease bookmark for where it was in reading the change feed. So we'll take a look at that now. This Leases container wasn't here when I started my demo. If anyone was paying attention carefully, I started out with 3 separate Cosmos DB containers. But this Leases container wasn't there. The Leases container basically has your bookmarks for where you were in last reading the change feed. We're going to keep 1 bookmark per partition, per basically microservice that reads from the change feed. So you don't actually need to go and manage the lease collection, but we're going to take a look at what's in there. If I look at this one document here, it's basically a bookmark for a particular partition for my alert microservice. So that email microservice that went and sent out emails, this is a bookmark. When I stopped my change feed, the change feed processor library went and bookmarked where I last was in reading partition 8's changes, and I bookmarked that, so if I were to go and start it again later on, I can just pick up where I left off. This is stored in just another Cosmos DB container, so very easy to manage, and Functions will actually go and set up this Leases container automatically for you. In general, you actually don't need very much throughput on this. I have 400 RUs provisioned. Even really large-scale workloads using the change feed aren't going to generally need more than a few thousand RUs for this. I actually go and prefix the ID value here with something unique for each of my microservices. So if you notice, this is prefixed with alert. If I come down and look at the other documents, they're going to be prefixed with other values. I've run my alert microservice, but I've also run the current location microservice. And I store these in the same lease collection, but I'm able to distinguish which is which by that prefix that I put before basically the Cosmos DB collections name. Let's take a look at the code now, go a little deeper. Take a look at that materialized view function and come down here. So the logic in this function is pretty simple. Just like with the email alert Azure function, every single time there's a write to Cosmos DB, we're going to go and trigger this. So every single time there's a write to the locations container, we'll trigger this basically tiny microservice here. Every time there's a change, we're going to loop through all the changes, go and take the flight number and make it the ID value of the document, and then go and write that and persist it in the current locations container. So the logic here is pretty simple. And the great thing is it's completely independent from our other microservice, the one that sent alerts for new emails. That lease collection prefix, the current location, is specified right here. So you'll specify that separately for each function. And this is how we're able to distinguish different functions' bookmarks from one another. So we have, again, separate bookmarks per microservice. And each of these bookmarks are completely independent from one another. They're stored in Cosmos DB, so they're stored in a high availability service. So you're never going to lose these bookmarks. They're going to be available with 5 nines of availability. And this is what makes the change feed processor library incredibly robust. Let's imagine in this scenario I have 3 partitions. When I started today, I created 1 microservice that has a bookmark for which document it's last processed. And as it processes more documents per partition, it's going to go and progress further down in reading from the change feed. Later on in this session, I added microservice 2, the one that went and sent out basically the materialized view, was triggered every time we did a write, and pre-computed the materialized view and persisted that back into Cosmos DB. This microservice has separate and independent bookmarks. So as microservice 1 moves along, or if I need to stop a certain microservice, these can each persist and continue to run independently from one another. And their only dependency is on Azure Cosmos DB, which is a highly available, highly scalable service. So 2 down, 1 to go. We built out 2 of the microservices for our application. We send alerts if an airplane enters a no-fly zone. And we also display a real-time materialized view of a different airplane's location that we go and call into with a web app. Next thing we're going to do is display the upcoming arrivals board. So you want to think of this as basically the arrivals board in the airport. When you go and you look at all the planes that are going to land in Orlando Airport, it's going to basically show that list sorted. Now, this arrivals board might not be limited to being displayed in airports. It might be displayed in air traffic control towers. Basically, think of this as something that also, just like our map service, that is going to be accessed very frequently. Now, hopefully this is an easy question. We have 2 options for building out this arrivals board. We can recompute what the arrivals board is every time we need to go and basically get that value. Or we can build out a materialized view that goes and persists the value of the arrivals board so that we don't need to go and repeatedly calculate it every time a service needs to access it. Which one do you think it is? You can just shout it out. It's B, right? Really, really simple. We can do this the same way as before. Now, of course, we'll need to do more processing here. Our function's going to be a little bit more complex. So in this case, we're likely going to want to have that same strategy where we make that ID value in this document something that is really something we can use to look up on. So we put MCO as the ID value. So if we want to do a read item async in Cosmos DB, we can look up this document by its ID value, which is MCO Orlando Airport, and then go and supply the airport partition key. So we'll basically know which partition it's in, and we know the ID value. So this read of Cosmos DB is just going to cost 1 RU. Now, in this case, we're going to be recomputing it every single time we run our Azure function. Now, for a lot of IoT applications or a lot of retail applications that use the change feed and basically build a materialized view that's real time, they cannot afford to have the materialized view really lag behind by more than a few seconds. If, for example, you had a gaming leaderboard, it has to remain pretty close to being perfectly up to date. It can't really lag behind by an hour. If it does, people aren't going to want to play your game because the leaderboard won't be up to date. Now, in this case, does it matter that the arrival board is perfectly up to date? It might. We don't know. Likely not in practice. For this example, we assumed that everything had to be in real time and the location of each plane had to be really precise. So for the map, it was important that it was in real time. In this case, for the arrivals dashboard, if it needs to be in real time, then you'd want to go and do that materialized view, build that materialized view using the change feed. And every time we do a write to the locations container, go and rebuild that materialized view. But of course, if this doesn't need to be in real time, you could have some sort of job run separate from the change feed and go and just issue a query every 5 minutes and then go persist that value somewhere. That would be another alternative if you do not have as real-time requirements. So we'll partition on airport for really quick lookups. And same as before, we'll go and persist this value in the arrivals container. So any web app that needs to go and access this is going to go call into arrivals container specifically. We can issue ad hoc queries against the locations container. But really, anything we need to go and access for our upcoming arrivals is going to go right to the arrivals container for 1 RU really quick lookups. So our app was successful. We built out an app that ingested data from different airplanes. We built out 3 microservices, which all did separate and independent tasks to go and basically build out our business software for our airline. After a few years of running the app that was super successful, we have accumulated over 10 terabytes of data. We've ingested a lot of data into the locations container, and we just left it there. Our airline is required to keep plane locations past history for an infinite amount of time, so we can never delete this data. So the development team decided to keep it all in that same Cosmos DB container, and after a couple years, it grew to 10 terabytes. What should we do? Any ideas? Yeah. Move it to blob storage, exactly. We're using the change feed very heavily, and we have 3 microservices here that have been running. But we want to add on another microservice, another Azure function that's going to basically go and read from the change feed and then do a write to Azure blob storage. We'll process the changes and the writes that are done to Cosmos DB and keep blob storage basically synchronized with Cosmos DB. We'll then go set a time to live, or TTL, property on Cosmos DB of, say, 60 days. So every time a document is written to Cosmos DB, the countdown begins. After 60 days, it'll automatically be deleted from Cosmos DB. But we'll have retained the data forever in blob storage. And it'll be much cheaper that way as well if you have, let's say, hundreds of terabytes or petabytes of data. So that all went well, and our app is successful. And for a while, we don't really do that much until the CEO's son of Contoso Airlines, the CEO, his son really wants a software engineering internship. So he's not a very good developer, but we decide to hire him. And he's messed up a lot of other pieces of code that we have. So we decided we're going to give him something really simple. We're going to have him update that email alert microservice. Instead of sending alert for no-fly zone over the Orlando Convention Center, we're going to update it to send alerts if you enter the no-fly zone, for example, near Orlando Airport instead. So let's go take a sneak peek into the changes that he made. Now, what this intern did was he came into the email functions, email alert function, and he went and looked for the no-fly zone here, the business logic that calculates whether the plane is in the no-fly zone. And he went and he made some changes. He couldn't get the email alert to work, so he decided to basically just go and make it really simple. Just say something like that. So we don't need to be experienced software engineers to know that every time this runs, it's going to say the plane is in the no-fly zone. And of course, he's been struggling his entire internship. So he's really happy about this. So he doesn't even test it out. He just goes and deploys it into production. So if I come back, I'm going to stop my current location microservice. I'm going to go and I'm going to run that email alert microservice. Any guesses what's going to happen? What will probably happen is Outlook's going to say you can't send any more emails and kind of lock me out for a little bit. So that'll run, and basically very shortly, I'm going to be flooded with emails here. And essentially, this is going to cause a lot of spam. We're going to be very unhappy, right? We're going to be sending alerts to people that say the plane is in a no-fly zone, things like that. And that's really not ideal. So we obviously need to go and take down that microservice very quickly. So that's basically going to run and process the changes as they're written and send a ton of emails. So it's going to be pumping out emails very, very shortly. Now, we obviously have to take that app down. And when we do that, we're going to really rely on that separate leases concept. So that idea of having separate leases for each container in Cosmos DB, or for each function in Cosmos DB, is super critical here. Obviously, there was an issue now with the email alert microservice, so we have to go and take that down, right? We need to stop that function and stop it from sending out alerts. But we still want the current location, and we still want the other microservices to continue to run as normal. The great thing about this microservices architecture is each microservice only has a dependency on Cosmos DB. Cosmos DB is a high availability service that gives you 99.999% availability. So you can take that dependency on Cosmos DB to ensure that your microservices architecture isn't as weak as its weakest link, whether that link is functions going down or some intern deploying bad code. Now, a couple best practices about reading from the Cosmos DB change feed. There's no cost for reading from the change feed. A lot of times, customers think the change feed is some premium Cosmos DB feature, and that's very far from the truth. It's a feature that every customer, every Cosmos DB customer, should really know quite well and really heavily use. It's really not much different than a regular read from Cosmos DB. And the change feed is enabled by default. So if you are one of our first Cosmos DB customers years ago, and you decided after the session you want to go and start reading from the change feed, you can go and do that. If the document is still in your container, it's still going to be persisted in the change feed. You can rewind the container to any point you'd like, whether it's the beginning or a specific time, and read it. That functionality, just as an example, is something that you don't get through Functions. Functions is designed as a simple way to read from the change feed. So these simple microservices that we built, Functions is going to be perfect. For more advanced control and functionality, I do recommend going and deploying the change feed processor library yourself, and you'll get capabilities like that as well. But all of this is very robust. No matter how you use the change feed processor library, you'll get those guarantees of high availability and at least one semantics. The change feed contains the latest version of every document. So in this case, we were doing writes to Cosmos DB. We weren't doing a lot of updates, right? We're just doing writes. So if we were to do updates, only the latest version of the document is going to be in the change feed. So that's really important to remember when you're going and reading from the change feed. For really robustness and guaranteeing you're processing every single change, you do want those changes to be writes. Intermediate updates and deletes, obviously, as I mentioned, are not in the change feed. For deletes, the pattern we recommend is setting an isDeleted property in your document. And when you want to delete the document, set isDeleted to true, and then set a document-specific time to live, or TTL, on that specific document. So it's going to be triggered. It'll trigger the change feed, trigger your Azure function when it's updated. And then after a specific amount of time, say 24 hours, it'll be deleted from Cosmos DB, and the delete will be processed. Now, we didn't talk at all about handling errors today, just because we only had 45 minutes. But this is obviously something that's incredibly important when you're reading from the change feed, especially if you're doing something like sending out email alerts or going and processing documents and writing them to another data source like Azure Blob Storage. If, for example, we were to have some error or exception in our function code, we would surely want to do that try-catch pattern where we catch the error and go store what document failed and store it in a queue somewhere so that we can go and later reprocess that document either manually or through some other code and go and perform that necessary business logic. This allows your function to continue processing later documents, but still retain which documents were not processed correctly so that you get the guarantee that you're processing every document that's written to your locations container. The big idea that I want to emphasize is when you're building out a microservices architecture and you're reading from the change feed in Cosmos DB, you want each specific function to have a separate and small independent task. So if I had wanted to in this demo, I could have combined the email alert microservice. I could have combined the materialized view microservices and the write to Azure Blob Storage microservices. I could have combined those all into one giant Azure function. But then what would have happened when we hired our intern? We would have been basically having to take our whole service down. So that's the advantage of this microservices architecture. And when you read from Cosmos DB's change feed to event source to these microservices, you get an incredibly robust and highly available and highly scalable solution. So I hope you enjoyed the session today. These are some upcoming Cosmos DB sessions to learn more. Definitely recommend these. They'll be led by my colleagues. The change feed examples and best practices from reading from the change feed are all in our new workshop materials. So if you go to aka.ms Cosmos DB workshop, and you click there, we have different labs available. There's a change feed specific lab that goes through the change feed in depth. And there's also a scenario-based IoT lab, which when you go through the lab, it's going to look a lot similar to the one that I ran, except it's going to be with cards instead of planes. So same best practices, and this will allow you to get hands-on with a lot of these concepts. So thanks for attending today, and have a great rest of Ignite. Out of the room. If I'm unable to answer your question now, I'm actually going to be going right to the Cosmos DB booth after this, and I'll be happy to cover it there. To incentivize questions, and for anyone that answered a question correct today, I have some socks. So feel free to stop by, and if I don't get to give you a